Right, so this is the last part of the mechanics and vector functions it's talked about. So we did vector functions previously when we looked at vectors themselves, and we looked at vector time varying functions. Certainly we had RT, things like RT, R dot T, those kind of things. But we can also have forces expressed in terms of functions as well. And so here's an example that talks about that. So we've got two forces, F1, which is 2i plus 3j, and F2, which is 3i plus 4j, and they act on a mass of 2, which is at rest. Find these things. Down here it says assume MKS, so MKS is our normal system that we use, meters, kilograms, seconds. So that means that these forces are newtons, the mass is 2 kilograms, rest is 0 meters per second. And the other thing that we're looking at here is that time equals 0 when we're starting to look at it, that v equals 0. Alright, I'm starting to waffle. So acceleration of the particle. So acceleration, as we know, the resultant force is the mass times the acceleration. And so now we've got these two forces. So 2i plus 3j. And we're going to add together 3i minus 4j. And that equals the mass, which is 2 times the acceleration. Let's add our vectors, so components. We've got 2i, 3j, so we've got 5 lots of I. Get a bit lazy, should put my vector signs in. And here we've got 3j and I'm taking 4, so that's minus 1. And that's 2a. So the acceleration then from that, then divide by 2 is 5 on 2i minus a half j. Alright, there we go. There's our acceleration. Alright, so now find the position of the particle at time t, given that initially it's at the point 3i to j. So t equals 0. Its position is 3i plus 2j. So we're going to use that later. Probably because we're going to integrate, of course, because we're going from acceleration back up the tree to position. So we're going to integrate to get there. So first of all, let's have a look. Part B. Alright, so we know the acceleration is there. So to get our velocity, we need to anti-differentiate. With respect to time, our acceleration. And so when we do that, there's no t's here, so that's 5 on 2t I minus a half tj plus some constant. Now what we were told is, right up the top here, forces act on a particle which is at rest. So at the start, time equals 0, v equals 0. So at t equals 0, v equals 0. And so just say, doing the calculation, that means that c in this case has got to be 0 as well. Alright, so now we have the velocity is 5 on 2t I minus a half tj, and that's it. Right, we're after position, so going back up the tree, anti-differentiate the velocity to get the position, the displacement. Ti minus a half tj dt. Alright, raise the power by 1 and divide by the new power. So we've already got a 2 down there, so 5/4. I minus a half of half, well it's going to be, I put a squared there for, I've got ahead of myself. Raise the power by 1, divide by the new power, and there's already a 2 there, so we want to put a 4. And then plus some constant. Alright, now the other bit of information that we were given in part B was that t equals 0, its position is 3i plus 2j. Alright, so t equals 0, its position is 2i plus 3j. So let's stick that in, so 2i plus 3j equals 5/4 times 0 squared I minus 1/4 times 0 squared j plus some constant. So the constant in this case must be 2i plus 3j. Alright, so let's, I think I got that right. No, 3i plus 2j. 3i plus 2j. Trying to remember too much at the same time. There you go, get caught, always need to double. So 3i plus 2j. 3, 2, 3, 2, 3, 2. That's better. Alright, so our position then is, alright, going to put it together. So in the I direction, we've got 5/4 t squared, and we've also got this 3. So 5/4 t squared plus 3. And in the j direction, we've got the minus 1/4 t squared and plus 2. So I'll go 2 minus 1/4 t squared. Alright, so there's our position vector. Now we could use r for that if we wanted to, rather than x, but that's fine. Alright, so next, the Cartesian equation of the path of the particle. Alright, so the Cartesian equation, of course, relates to, well, if this is our position of our particle, and I probably should have used r, but anyway, not to worry. So if that's our position, then our position changes with time. And the Cartesian equations, this would be our x and this would be our y. So in terms of, and time is of course our parameter, so 5/4 t squared plus 3, and y equals 2 minus 1/4 t squared. And so what I'm going to do, take 3, and then times by 4, divide by 5. And that's t squared, and so I'm going to take that and I'm going to put it in there. So y then is equal to 2 minus 1/4 of 4x minus 3 over 5. 4's cancel, so y equals 2 minus x minus 3 over 5, and we can fiddle around with that a bit. Let's have a look. So we've got y equals, so 2 would be 10⁵ minus x minus 3 over 5. So we've got 10, so we're subtracting all of that. So minus x, minusing the -3 over 5, and so we've got 10 minus x, oh, not 10, 13. 13 minus x, because 10 plus 3 is 13, minus x over 5, y equals, and there's our Cartesian equation of the path of our particle. Alright, so that's all we're referring to. We've done that sort of thing before with other vectors, vector functions, particularly involving time. So there's not much in the way of any difference other than the application of them. Okay, so if there's anything in there you need clarifying, make sure you get some assistance if there's anything in there that you need help with. And as always, have fun.